So this is what we were doing last time, guys. We started saying that the state properties of an ideal gas would be internal energy. And then we said, how does an internal energy for an ideal gas behave when you have different situations like constant velocity, constant volume, constant pressure, constant temperature, and for adiabatic transformations. And we developed these. So all of these things are important. Then we did heat capacity, also very, very important. We derived it. And we said there were two different kinds of systems, one for constant volume and one for constant pressure. And we derived these. This is something you have seen before in chemistry. Yes. Now, we developed CV for a monoatomic, for a diatomic, and for a polyatomic ideal gas. Okay, so starting here, when we think of the monoatomic ideal gas, how do you think that changes if I was to write, wrong. Pick a color.
Purple. Blue.
No, blue is good. No, blue is good.
Blue.
Okay, here we go. So if I was to ask you for CP for a monoatomic ideal gas, how do you think we would do it? We have that equation. I'm going to call it the star equation. How do you think we should do that? We take the value of CV and we add NR to it. What do we get? 3/2 plus 1? There we go. If I talk about the diatomic ideal gas, how do you think I will find the CP value? The heat capacity at constant pressure. Yep. What will be the answer? The 5/2 NR plus NR will give me, there we go. And the CP for a polyatomic ideal gas will just be, there we go. Thank you. Okay, are we good with this? Now, what you may have seen is heat capacity per mole. So heat capacity per mole. And you would have seen this written as CP equals 5/2 R, CP equals 7/2 R, and CP equals 4R. So that is a common way of writing it, but I wanted you to see the other version before I showed you this version, because most textbooks write it per mole. Okay, so another thing that we need to talk about, I put a line here, is the relationship between CV and CP. So the relationship between CP and CV was CV plus NR, correct? Where N is usually either written as N over NA, where what is NA? Thank you. And the value, numerical value is? And in this case, the Avogadro number will be molecules per mole. And number two, the relationship that we need to know is called the specific heat ratio, which is Cp over Cv, and it is represented by a gamma. Put this in a box, actually double box this equation. It is that important. It is also in textbooks called the adiabatic exponent. For a monoatomic gas, gamma is 1.67. For a diatomic gas, gamma is 1.4. And for a polyatomic gas, gamma is 1.33.